there's a big scary fraction and we have to integrate it or something like that, or maybe do binomial expansion and it's really scary and big. But don't worry, because this scary monster is actually inside there. We can shrink him down. He's not that scary at all. Look. Oh, he's tiny. He's gone. And revealed are these cute little ones. Ooh, cute little fractions that are really easy to deal with. Okay, so what we're doing is we're going to take the big scary fraction and we're going to learn how to write it as 3 cute little easy fractions, and then never again will you be frightened of integrating a big scary fraction. So essentially what we're doing here is on adding, because you can imagine being given this question in C3 and being asked to add these up and simplify, and going in this direction and ending, make the denominators the same and add them all up and end up with that. And that's called adding fractions. And what we're doing in this exercise is we're going the other way. We're going to on-add these fractions. And these cute little fractions that we end up with down here, the cute small ones, they are called partial fractions. So the process of doing this is usually called partial fractions. That's what you'll see in your book. I'll write the big scary fraction in partial fractions. So that's what we're going to learn how to do. The first question is, how do we know what these cute little fractions are going to look like? Well, we can look at the bottom. Okay, we've got an x squared here and we've got an x plus 1. So some fractions were added up. Actually, there's going to be 3, not 2, even there's only 2 things here. I'll explain why. But it's pretty obvious what they were, right? One of them's come from x plus 1 and one of them's come from x squared in the denominators. So the denominator must have been x plus 1 and the other denominator must have been x squared. And then what somebody's gone and done is they've multiplied top and bottom of this one by x squared, and they've multiplied top and bottom of this one by x plus 1, and that's why we've ended up with x squared, x plus 1 in the denominator. And that is true, but for all I know, there was another one which just had x in the denominator. That might have been there. And it's kind of like with the plus c in integration. It might have been there, it might not have been there, but we certainly have to take it into account when we're planning. So if that one had been there as well, then I would have been able to create the same denominator, x squared, x plus 1, by multiplying by x plus 1, x plus 1 on the top and the bottom. And then what that would do on the bottom of this fraction is it would create that x squared, x plus 1, which is the same denominator as all the others. So there's actually 3 factors, 3 fractions that have been added up. Now I have no idea how many of them there were, I have no idea how many of them, and I have no idea how many of them, but at least I've got an idea of the structure, so I can work from there to work out how many of each fraction I had. So I've got my structure sorted. I know there's going to be some, well, I don't know, but there's probably going to be some x's that would be made into x squared, x plus 1 by multiplying top and bottom by x plus 1. And there's something over x squared, which would need an x plus 1. And there's something over x plus 1, which needs an x squared. Okay, so what would happen if I actually did add these up as they are at the moment? I would get ax, x plus 1, plus b, x plus 1, plus c, x squared, and that would all be over x squared, x plus 1. Okay, so my denominator is correct, good. What I need to do is work out what to choose a, b and c to be in order to link it up with the correct numerator, which is 7x squared plus 2x minus 1. And there are 2 main methods for doing this, and I will show you both of them so that you can choose which one you prefer and go with that one. So here's method 1. which is what I call the sneaky X method. So let's look at how far we've got. We know we've got the bottom sorted, that's right. It's the tops we've got to look at, the numerators. So let's just have a look at that as an equation in its own right. 7x squared plus 2x minus 2 has got to be what we get when we choose the A and the B and the C correctly, and so that all these add up to that. Now, if all of these are going to add up to 7x squared plus 2x minus 2, then they have to add up to that when x is 0. They have to add up to it when x is 1, they have to add up to it when x is 2, they have to add up to it when x is minus 1, they have to add up to it when x is a billion. They have to always add up to it. This has to be true for all x's, and that's the key thing I'm going to exploit. So if it's true for all x's, then it must be true when x is 0. Let's have a look at what the left-hand side is when x is 0. Well, that's easy, it's minus 2. The right-hand side will be, well, it's just, what's it going to be? I think if x is 0, we literally just get b, because the cx squared will be 0, the axx plus 1 will be 0. So, and then in here, we'll get b 0 plus 1. And so I found b. Hooray! That was really easy. So b is sorted. So that's the thing, is you can use any x at all, but if you choose the right sneaky x, you get what you want. So what about another sneaky x? What about choosing x is minus 1? Okay, bit more complicated. 7 lots of minus 1 squared plus 2 lots of minus 1 minus 2 on the left. And on the right, we've got a lots of minus 1 times minus 1 plus 1. Oh, that's going to go. Plus b lots of minus 1 plus 1. That's going to go as well. Plus c lots of minus 1 squared. Okay, let's be careful with minus signs here. 7 minus 2 equals c. So c is 3. Hooray! Okay, I wonder if there's any more sneaky x's that I can choose. Well, no, there aren't, because those ones I chose, because you can choose anything, but I chose x minus 1 to make these two disappear, and I chose 0 to make these two disappear, but there's nothing I can choose to make this one and this one disappear, the last two, because that both those factors are in with the a. But let's just have a look where we are. Let's take stock. What have we got? 7x squared plus 2x minus 2 equals don't know amount of x plus 1 minus 2 lots of x plus 1 plus 3 lots of x squared. Okay, now this is true for any x at all, so it must be true for x is 1. This isn't going to be particularly sneaky, but can still use x is 1. Let's see what we get. 7 plus 2 minus 2 equals a times 1 plus 1 minus 2 times 1 plus 1 plus 3 times 1 squared. X is 1. This gives us 7 equals 2a minus 2 times 2 is 4 plus 3. So 8 is 2a, a is 4. So there we go, we've done it. A sneaky choice getting us the first one, another sneaky choice getting us the second one, and then fairly arbitrary choice, I just chose the one because it was easy, to get us the last one. And we know what a, b and c are. Method 2, comparing coefficients. So let's look at that top line again, because we know we've got the bottom sorted. 7x squared plus 2x minus 2 has to always equal ax x plus 1 plus b x plus 1 plus cx squared. Let's expand out that right hand side. Ax squared plus ax plus bx plus b plus cx squared. Let's tidy it up a little bit. How much x squared have I got? A plus c. How much x have I got? A plus b. What else have I got? A b. Okay, comparing coefficients is, well, literal compare coefficients. Coefficients are numbers in front of. So for example, the number in front of x squared is 7. So given that these are the same, the number in front of x squared must equal 7. And the number in front of x is 2. So given that these are the same, the number in front of x must equal 2. and the number on the end, the coefficient of no x's, is -2. So given that these are the same, the number on the end here must be equal to -2. Okay, b is sorted, b is -2. I can sub that into the coefficient of x. If b is -2 and a plus b is 2, then a minus 2 is 2 and a is 4. And if a plus c is 7 and a is 4, then c is 3. So there we go. We've got the b is -2, the a is 4, and the c is 3. Two methods. You can do both or choose your favourite. So what have we learned? The big scary fraction can be broken up into 2 or 3 cute little fractions. First, you set up the shapes of the cute little fractions by looking at the factors of the denominator of the scary fraction and putting them into their own individual cute little fractions. Then add up the cute little fractions, just using a's and b's and c's on the top. And then either use the sneaky x or comparing coefficients to find the values of those constants.